In this presentation, we'll discuss proper and improper transfer functions. We'll also examine why physical systems do not have improper transfer functions. First, let's define proper, strictly proper, and improper transfer functions. So let's suppose we have a transfer function g of s, which is the ratio of two polynomials. The order of the numerator polynomial is m, and the order of the denominator polynomial is n. A strictly proper transfer function has the order of the denominator n greater than the order of the numerator m. A proper transfer function has n greater than or equal to m, and an improper transfer function has n less than m. In other words, an improper transfer function has a numerator of greater order than the denominator. Now that we've defined these terms, let's discuss why physical systems will not have improper transfer functions. To illustrate the reasons, let's consider the simplest improper transfer function, and this would be the differentiator, which has the transfer function g of s equal to s. So the numerator is a polynomial of order 1, and it's simply s, and the denominator is a polynomial of order 0, and it's simply 1. So the relationship between the input and the output then is y of s is equal to s times x of s. So the transfer function is s. Now if we now inverse Laplace transform, we find the relationship that y of t is equal to x dot. So the output is the time derivative of the input. This kind of relationship is not physically possible for several reasons. The first objection that we have to improper transfer functions arises out of common sense, and it has to do with the relationship between inputs and outputs that a transfer function is. For a system, the input is the cause of the change of the output. So, if a differentiator were a legitimate physical transfer function, it would be saying that the derivative of a physical quantity changes because the physical quantity changes. That goes against our common sense. For example, an object's position changes because it has a non-zero velocity, but it's not the other way around. The cause of an object's velocity changing is not the position. The cause of the object's velocity changing is a force acting upon the object. Our second objection to improper transfer functions has to do with the power relationship between the signal input and the signal output. So let's consider the following signal. X of t is cosine t minus 1/3 cosine 3t plus 1/5 cosine 5t minus 1/7 cosine 7t, and so on. It's easy to show that this is a finite power input. And when we put that into our system and take its derivative to form the output, we find it is minus sine t plus sine 3t minus sine 5t plus sine 7t, and so on. It's easy to show this is an infinite power output. So a finite power input yields an infinite power output. But it's worse than that. Note that y of t is periodic, and recall that for a periodic signal, we can evaluate the power over one period. Since the power is infinite, this means it achieves infinite power in finite time, within the period of y of t, which is only 2 pi seconds. So we have a finite power input yielding an infinite power output, and that infinite power is achieved in finite time. Now, we should note that any unstable system can also yield an infinite power output in response to a finite power input. That's one of the properties of being an unstable system. We don't have bounded input, bounded output stability. But the key thing here is that the infinite power output doesn't achieve infinite power until time goes to infinity. So it's not achieving infinite power in finite time, unlike the improper transfer function. Let me provide an example to illustrate this point. Suppose we have the input x of t is a unit step. That's a finite power signal. And we put that into the system g of s equals 1 over s, what we call the integrator system. And we find the output, and we'll call that y of t. That y of t is going to be t times u of t, which is the ramp signal. Now, the ramp signal has infinite power, but it's finite power over any finite time window. It doesn't achieve infinite power in a finite time. On the other hand, the output of y equals x dot can achieve infinite power in a finite time. So the physical objection here has to do with going to infinity in finite time. The unstable proper system won't do this, but the improper system can do this. Our final objection to improper transfer functions has to do with noise amplification. All physical quantities are subject to some thermal noise, and these are random fluctuations that are completely uncorrelated from one moment to another. The technical term would be white noise. When we differentiate such a signal, this would produce an output with infinite amplitude. Since we naturally object to a physical system producing an infinite amplitude output, we have still another reason not to consider improper transfer functions. Let me close this presentation by noting that improper transfer functions can appear as parts of a larger model. They just can't be physical systems in and of themselves. So, for example, we might have a system that has variables z, x, and y, with x being the input and y being the output. The equations relating these are y is equal to z dot. That is an improper relationship. And z double dot plus z equals x. That would give the transfer function between x and z as 1 over s squared plus 1, which is strictly proper. The transfer function between x and y, then, would be s over s squared plus 1. That transfer function is strictly proper as well, and if x and y are the physical variables, then this transfer function is physically realizable. We could, however, write these equations as a block diagram in the form seen at the bottom of the page, and you'll note the transfer function between z and y is improper, but the transfer function between x and y is strictly proper. So in terms of physical variables, we have a proper transfer function, although we have an improper transfer function between this variable z and the variable y.